In standard electrical engineering, scaling power output is a matter of brute force. You linearly increase mass, friction, or combustion to force a higher yield. But magnetic gravitational, or Magrav systems, abandon that mechanical friction entirely, instead operating in favor of continuous fluid field dynamics. The engineering objective for the Oasis Project is to construct a pyramidal plasma generator capable of sustaining continuous outputs between 10 and 50 kilowatts. Attempting to hit that target by measuring standard electron vibration is a structural design error. This system does not operate on traditional electrical current. The blueprint requires a precise convergence of material state, geometric ratios, kinetic rotation, and specialized extraction protocols. On the left, you see standard linear electron flow. On the right, a plasmatic energy network operating through 4 interconnected nodes. This generator does not consume fuel to run. It operates as a dynamic, multi-dimensional ecosystem that requires highly specific tuning. To successfully scale output in this framework, engineers must discard the assumption that raw physical mass equates to power, and instead focus entirely on field mechanics. The primary nodes of this generator consist of spherical containment units. The physical composition of these outer shells, whether molded from plastic, copper, or standard ping-pong balls, has zero effect on the field. The only active variable is the internal state of the material placed inside, the GANS, or gas in a nanosolid state. A common point of failure in system design occurs when the CO2 GANS is allowed to dry into a white powder. Once desiccated, the material completely loses the dynamic magnetic field necessary to induce plasma generation. It becomes totally inert. Power in this context is a function of the gradient, the tension between the gravitational center and the magnetic boundary. Dry powder is static, offering no internal flux to drive a field, regardless of how many kilograms you pack into the reactor. Retaining the GANS in a liquid state allows for a continuous internal exchange, where heavy elements sink to form a gravitational core, while lighter elements generate outward magnetic pressure. It is this high-density interaction that induces the field strength necessary to exceed 15 kilowatts of output from a mere 10 grams of material. Blending these specific atomic weights creates the outward field pressure required to manipulate the size and strength of the generated energy. Consider how the human body runs a marathon. It converts a highly efficient, small intake of food into a continuous GANS state to sustain motion. It does not combust liters of heavy diesel. Output capacity is dictated strictly by the dynamic state and gradient mixture of the internal material, not the sheer volume of mass you pack into the shell. Once the internal materials are properly balanced, the nodes must be arranged physically. Builders should avoid locking the design to arbitrary, static measurements, such as a standard 100mm gap between units. Spacing is dictated strictly by a ratio derived from the exact diameter of your chosen containment spheres. Construction follows a set sequence. Set the 3 base centers to establish the foundational footprint, then calculate the elevation of the final hovering sphere using those exact sequential proportions. This establishes a perfect tetrahedron. Structurally, there is no true upper or bottom reactor. Any node can function as the apex depending on your orientation. Locking in these precise relative proportions generates the central field force within the void. Verifying the existence of this field requires highly specific observation tools. Standard unidirectional Gauss or Tesla meters are ineffective. They are built to read linear electrical surges along a single axis. Reading a spherical volume of plasma requires 3-dimensional gradual field detectors, equipment currently in dedicated lab development. Applying static spatial measurements and unidirectional electrical sensors to this array will yield zero useful data. They are structurally blind to relative, multidimensional geometry. The next major requirement is kinetic. To activate the system, the individual containment spheres must be mechanically rotated. Laboratory baselines indicate the system should be initialized by bringing the motors up to 2,500 RPM. As the fields engage and stabilize, the optimal operating bandwidth will naturally settle between 2,000 and 2,500 revolutions per minute. Hardware routing must accommodate this. The 3 base motors share a single power supply, while the top motor requires an independent, isolated circuit. The elevated node hangs freely and experiences zero downward structural pressure, requiring entirely different power management than the loaded base units. When the generator hits its operational bandwidth, a pocket of concentrated free plasma materializes in the geometric center, exerting outward pressure vectors against the spinning spheres. At this stage, you will physically hear the pitch and speed of the motors drop and surge. As the free plasma shifts its internal position, it applies resistance to different nodes, dropping one to 1900 RPM, while another speeds up to compensate. These RPM fluctuations are not mechanical errors. They are the active indicators of an ecosystem balancing its shifting field forces. The engineer's role is strictly to provide the initial kinetic rotation. After that, the ecosystem governs its own equilibrium. Once the field achieves stability, the energy must be extracted to supply external kilowatts. Do not attempt to wrap the generator in standard three-phase coils or alternating current alternators. Applying standard electrical extraction methods will act as a dampener, destructively interfering with the continuous monofield generated by the GANS. Extraction requires an explicitly designed direct current half-sphere winding that completely envelopes the generator array. The interior void of this coil must measure exactly 21 centimeters across to accurately interface with the focal point of the tetrahedron. It is an incredibly dense component, requiring 5 to 6 kilograms of pure, continuously wound copper wire. Fabricating this specific half-sphere structure is highly complex. The original laboratory prototype required 2 years of dedicated specialized development to finalize. The scale and precision required for this single extraction component separates casual hobbyist builds from rigorous applied engineering. Tapping into multidimensional energy mandates bespoke architectural shielding. Off-the-shelf electronics will simply choke the field. The final functional generator relies on 4 synchronized elements: a dynamic state material, balanced by tetrahedral geometric ratios, activated by auto-regulating kinetic motors, and harvested through a custom DC half-sphere coil. The Oasis Project requires engineers to tune this entire assembly as a responsive ecosystem. Forcing linear electron vibration through it will cause failure. Moving this architecture from a theoretical blueprint to practical, standardized research requires formal study. To facilitate this transition, the Spaceship Institute has formalized its academic programs. They offer 1 to 3 year executive master's tracks out of their Bara University location. The curriculum requires rigorous daily engagement, operating with a flat tuition fee of €6,000. Mastering plasmatic systems is leaving the realm of isolated garage experimentation and establishing itself as a formal, institutional scientific discipline.